Hi everyone, today we're going to talk about the Wittig reaction. The Wittig reaction is a really classic carbon-carbon bond forming reaction in organic chemistry. It's a very, very important reaction. It's been used for years, and what it does essentially is convert carbonyls to carbon-carbon double bonds, accompanied by loss, importantly, of triphenylphosphine oxide. The loss of triphenylphosphine oxide, a very stable compound, is part of the thermodynamic driving force to push this reaction forward. And you can see some examples. The Wittig reagent is composed of a positively charged phosphorus attached to a carbon ion, and that carbon ion is your nucleophile, which reacts with your electrophilic carbon. That carbon-carbon bond then becomes your double bond upon loss of triphenylphosphine oxide. So that's the general overall process that occurs. Let's break this down into mechanistic steps. So the Wittig reagent, as you can see, has shown here. The Wittig reagent we're going to use as 3 phenyl rings that you can abbreviate as triphenylphosphine PPH3 and attached to the carbon, which is negatively charged, which is an Ylide. So an Ylide is a compound where you have positive and negative charges on adjacent atoms. So the Wittig reagent is an Ylide. That makes the carbon negatively charged and gives it nucleophilic character, enough nucleophilic character to react with an electrophilic carbonyl carbon to form a new carbon-carbon bond. Okay, so you can draw a resonance structure of the Wittig reagent in which you have a C double bond P. And that's fine. And notice phosphorus there is neutral. Phosphorus with 3 bonds or phosphorus with 5 bonds is neutral. When phosphorus has 4 bonds, as shown in the typical Wittig reagent, it has a positive charge, just like nitrogen, which is right above it in the periodic table. So phosphorus with 4 bonds is positively charged. That helps stabilize the carbon that's attached to it to have a negative charge. Okay, so here's how we make the Wittig reaction. The first step here is typically called the Arbuzov reaction, and all that is an SN2 reaction. Triphenylphosphine is nucleophilic. You have the lone pair electrons in phosphorus that displace the alkyl halide. Typical SN2 chemistry. All the rules for SN2 reactions apply. That forms a phosphonium salt. Again, note that phosphorus has 4 bonds, so it's got a positive charge. And then what we do is, in step 2, deprotonate on the carbon that's attached to phosphorus to form the stabilized Ylide, where you have a positive and negative charge next to each other. People use butyllithium. You're going to use sodamide. These are strong bases. They're typically used to form the Ylide, the phosphorus Ylide, after the Arbuzov SN2 step. Okay, so now we've got our Ylide, and we're going to react it with the carbonyl and see how we form our alkene. So, as mentioned, the carbon ion reacts with the carbonyl carbon, and that forms a structure called a beta-ene. The beta-ene has a negatively charged oxygen and a positively charged phosphorus. Phosphorus is very oxophilic. Phosphorus and oxygen like to bind to each other. If you leave triphenylphosphine, for instance, out in the air, it will slowly form triphenylphosphine oxide. So the phosphorus and oxygen will bind, and that will result in a 4-membered ring called an oxophosphatane. And the oxophosphatane is going to break apart in step 3 because it's a 4-membered ring, and because breaking that 4-membered ring allows us to form the very stable molecule triphenylphosphine oxide. And in doing that, we get our alkene. You just in a mechanistic step where you draw 2 arrows to make your PO double bond and your CC double bond. And so that's the Wittig reaction. That's the mechanism. Okay, a limitation is that you can form, in many cases, mixtures of stereoisomers. There are ways to get around that. If you take advanced organic chemistry, you'll learn all about that. Typically, we typically assume that the E or trans isomer is the major product because it's thermodynamically more stable. But there are much more, there have been many advances made in Wittig chemistry and related chemistry to allow for control over stereochemistry. Typically, and in your reaction, you're going to get mainly in your lab the E or the trans isomer. The Wittig reaction, of course, has been used, as we mentioned, for many years to synthesize many wonderful natural products. So here's synthesis of beta carotene, the last step to make beta carotene shown at the bottom there. Okay, so if you see an alkene, such as compound A, and you want to make it, you want to synthesize that compound using a Wittig reaction, and this is very important. Just envision one of those two carbons, part of the carbon-carbon double bond, as a carbonyl, and envision the other as an ylide, okay, a carbon attached to phosphorus. All right, which you choose can be sometimes very important. Sometimes it doesn't matter. Okay, let's look at the two possibilities. In possibility one, we use the ring carbon, the cyclopentyl carbon double bond as the carbonyl, and we use the ethyl carbon on the right side as the one attached to phosphorus, and that's perfectly acceptable retrosynthesis. Possibility two, just the opposite. Again, that's acceptable. Which is preferred? Which is preferred in our synthesis if we're going to make compound A? Well, I would choose possibility number one, because you can make that via the reaction of a primary alkyl halide in the Arbuzov SN2 reaction. Okay, and primary halides react more readily in SN2 chemistry than secondary halides. And remember, tertiary halides don't react at all. Would it be wrong to make compound A in the previous slide by possibility two? No, it wouldn't. It would be wrong, however, if you tried to do the Arbuzov reaction with a tertiary halide. Remember that that's a very fundamental concept of sophomore organic, where you can't do SN2 chemistry on tertiary halides. So an advantage of the Wittig reaction over other eliminations, and you see an example in a Grignard reaction, is that you can control exactly where the double bond goes. Look at the elimination, the dehydration of the tertiary alcohol in the Grignard reaction shown, and you get the double bond in two different positions. You're going to get a mixture. Whereas in the Wittig reaction, you know exactly where the double bond's going to go, and you can predict that because you know your mechanism. So some things to consider is what are some advantages, what is the main advantage really of the Wittig reaction as compared to E1 or E2 eliminations and forming alkenes? Why can or can't you use a tertiary alkyl halide as a reacting partner to form a Wittig reagent? And you really need to know all of the steps in creating the Wittig reagent and then using that to form an alkene. And you should also be well aware of how to do retrosyntheses of alkenes and then forward syntheses of to make the alkenes using Wittig chemistry. There are some good problems there in your lab manual about that. And take a look at the video, the link to the little video here. It's just takes a few seconds to watch, but it'll show you a really nice snapshot of a Wittig reaction. Okay, have fun in lab.